Okay, here's my thinking on the Chapter 10 test. So number one, they just wanted a nomenclature for the given structure. So for this first structure, I numbered it right to left, and it's hex. Yeah. Triple bonds at carbon 3, so it's ine. So I got hex 3 ine, and then the substituents, we have 2 methyls on 2, and we have a methyl on 5. So this is 2,2,5 trimethyl hex 3 ine. Or another way you could name it would be 2,2,5 trimethyl 3 hexine. But I'm trying it a different way this time. Okay, next one, I numbered it right to left again. We've got, again, a triple bond, so we've got at 2, so we got 2 ine, that's his hex again, hex 2 ine, and then we have 2 substituents both on 4, so this is 4,4 dichlorohex 2 ine. Then the last one is just straight up hexine, or hex 1 ine, or 1 hexine. Any of those would have been fine. Okay, the next one, so we're starting with a starting molecule. Again, all of these are alkynes, and then we're asked to predict products. So for this one, reacting with ozone, on a terminal alkyne, you're going to get a carboxylic acid and carbon dioxide. So we've got, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4 carbons on the carboxylic acid, and 1 on the carbon dioxide. Going this way, got a strong base, and we're going to add propyl chloride, so we should see 3 additional carbons on the terminal end of the alkyne. So there's my answers for the first one. The second one, let's start with chlorine. We're going to add chlorine across the triple bond, so that's going to give us anti-addition of the chlorines, turning the triple bond into a double bond. And then we've got hydrogen. They didn't say excess, so I'm going to write both excess here, so that would get rid of our triple bond altogether, keep all of our carbons. So we got 1, 2, 3, 4, 5, 6. So we got hexane. Or if it was, they didn't say Lindlers, but I think I first drew this out with Lindlers. I'm thinking they wanted this product here, just the hexane. And then the last one, going to the right, again, this is acid catalyzed hydration, so we're going to turn this into a ketone with our double bond coming off of the more substituted carbon here. So here's our ketone, ignore that scribble. And then going the other way, this is hydroboration oxidation, so this is going to turn our alkyne into an aldehyde with the double bond on the less substituted carbon, so here. So we've got 1, 2, 3 carbons, 1, 2, 3 carbons, and then that's our hydrogen on the end. So that was the first couple questions. Next couple questions. Oh, number 3. Okay, so this was the all the different products if you're going to react a terminal alkyne with different reagents. The first one, though, it was turning, or what would be the starting molecule if you're going to react it with excess base and water to get this terminal alkyne? And I have this as our answer. So X being, I would say any halogen, chlorine or bromine or iodine. And the next one, we got 2 arrows, so it's going this way with excess strong base to give us the terminal alkyne, or going this way with excess HX. So the answer that I have is this this molecule here, which we have both of the halogens on the same carbon. So that would, again, if we reacted this with excess HX, we'd have 2 X's added to the more substituted carbon. And then if we subjected this to strong base, excess strong base, it would both of these weaving groups would weave and give us a triple bond on the terminal side. Okay, reacting with just one HX to this terminal alkyne would give us this product here. Again, with X on the more substituted carbon. Again, here we have, this is acid catalyzed hydration, so we're going to form a ketone with the double bonded oxygen on the more substituted carbon. Here we've got, again, hydroboration oxidation, so an aldehyde being formed. The double bonded oxygen on the less substituted carbon. Here we have just X2, so that's going to be cis addition. Or no, it's going to be anti-addition. So anti-addition of a halide, like our halogen, like again, X's could be chlorine, bromine. Excess X2 would give us this alkane with all of these substituents on both the carbons. Next, we have ozones. Again, on a terminal alkyne, ozone with water is going to give you carboxylic acid and carbon dioxide. And this next one, we're adding excess base and we're adding RX. So that's going to turn our terminal alkyne into acetylene, or maybe not acetylene, but no longer a terminal alkyne. So then if we did just hydrogen, excess hydrogen, that would give us our alkane. If we did hydrogen with Lindlar's catalyst, that's going to give us the cis addition of the hydrogens. And then if we do the dissolved metal catalyst, or the dissolved metal reduction, that's going to give us our trans addition of hydrogen. Okay, that was number 3. Number 4. Okay, this said, what is compound X if when treated with excess hydrogen gives us 2,2,6-trimethyl octane? So here's 2,2,6-trimethyl octane. I think we have 3 possibilities here if we're going to have excess hydrogen added to any 3 of these. Any 3 of these would give us this product. So I got the triple bond on this case on carbon 3. In this case, I have it on carbon 4, and here I have it terminal on carbon 1. And for all of these, we would have one stereo center, and I have that marked here with a dot. Number 5, similar to number 3, except now they want reagents, so they gave us all the products. So starting with our terminal alkyne here, so I'm just going to work from above and around the clock here. So this product could be achieved by adding just 1 equivalent of HCl. This product would be just 1 equivalent of H2. This product, that's our carboxylic acid, that would be ozone and water. This product, that's our ketone, so that would be H2SO4, water, and HgSO4 is our catalyst. This is our aldehyde, so that's, again, hydroboration oxidation, so that's BH3THF with hydrogen peroxide and our base, NaOH. This is, we got the addition of 2 bromines on the more substituted carbon, so that's going to be 2 equivalents of HBr. And then lastly, we've got our alkane, which would give us 2 equivalents of hydrogen and a palladium catalyst. So that's number 5. Number 6. Again, they gave us names. They want us to draw the structure. They started with 2 heptines, so I've got, 7 carbons. 1, 2, 3, 4, 5, 6, 7. I got my triple bond on 2. 2,2-dimethyl-4-octine, so we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons, methyls on 2 methyls on 2, carbon 2, and then our triple bond is on carbon 4. And then we've got a cyclodecyne, so we've got 10 carbons in a ring. We've got our triple bond on carbon 1 and our 2 ethyls coming off of carbon 3. That was 6. Number 7. 7 had multiple different reagents, and so starting with our our starting molecule here. If we're going to hit it with excess base, that's going to get rid of our bromines, and that's going to give us our alkyne here, our terminal alkyne. And then if we continue to use this base, that'll deprotonate this hydrogen on the end. And then we're going to add ethyl to that terminal alkyne. So that will give us this, and then we're going to hit it with Lindlar's and hydrogen, and that'll give us this this cis addition of hydrogen as our final product. For B, again, we've got acetylene here, and we're going to deprotonate one side and add a methyl, and then we're going to come in, and this is the hydroboration oxidation. So this is going to turn us into turn our molecule into an aldehyde. So that would give us double bonded oxygen on the less substituted carbon. So we have an aldehyde as our final product here. Similar here, we've got, again, strong base. We're going to add an ethyl to one of the sides, which I've drawn here, and then we're going to do acid catalyzed hydration. So we're going to turn this into a ketone with the double bonded oxygen on the more substituted carbon here. And then finally, strong base with a methyl added to one side and strong base with an ethyl added to the other side. And then we've got our metal, liquid metal reduction. So we've got trans addition of hydrogen. So we're going to keep our pi bond. So we're going to go to a double bond here between the two carbons. All right, that was 7, 8. 8, the last question. So you've got this sequence here. What they're wanting us to do is fill in the picture, or the picture for the different molecules. So starting with C6H12. Actually, this is what we had to end with. I thought it was easiest to work our way backwards from here. So if this is our final molecule, and it was reacted with ethyl iodide, then D must have been this ion here, this alkanide ion. So the alkanide ion is D, and then C would have been the molecule prior to this. It was just hit with strong base, so this would be a terminal alkyne. So a terminal alkyne reacted with this strong base followed by ethyl iodide would give us this. So this is D, this is C, and then B, it was a molecule that was turned into this, but it was reacted with a strong base and water. But then, again, it had bromine in it too. So going backwards from this, I have bromines on opposite carbons, which means that C6H12 was this molecule here with our double bond on the terminal, on one of the ends here. So we have hexene reacted with the bromine, gives bromine anti-addition across the pi bond, and then with the strong base and the water gave us the alkyne, and then with the strong base and the ethyl iodide gives us the final product. And that's 8. And that was the Chapter 10 test. All right, hopefully that went well.